So now we're going to have a look at another question from the waves and thermodynamics topic. So this is a heating question. This is a question on thermals. So we're told a vat of 250 kilograms of hot molten lead. So this molten lead is at 450 degrees Celsius, needs to be cooled to 380 degrees Celsius. We're told it's going to be achieved by mixing in cooler molten lead, 330 degrees Celsius, which is just above the melting point. The melting point of lead is about 325 degrees Celsius, to my understanding. We are asked how much lead must be added to achieve this result. All right. So we have some vat. It has some amount of lead in it, 250 kilograms, in fact. And it's all 450 degrees Celsius. This is too hot, so some other vat is going to have its contents poured in. This, we don't know how much we have to add, but we know that this is going to be 330 degrees Celsius. So this is a relatively simple mixing problem. Now in this particular mixing problem, when we think about the final mixture, it will essentially mix together and reach a uniform temperature. In order for this to be the case, we need Q to be equal to Q. So we need the temperature that the high molten lead loses to be equal to the temperature that the cold molten lead gains. So these are the thermal constants, Q, when we're thinking about heat mass and specific heat capacity, right? So that's what we're going to be dealing with here. So let's have a look at how this works. So in order for the heat losses from the hotter lead to be equal to the heat gains from the colder lead, we are going to have heat losses. So this will be negative. So we will have minus m times C times change in temperature is equal to plus m of the cooler lead times C times change in temperature. So this is change in temperature of the hot lead, change in temperature of the cold lead. Essentially, you're going to mix them together. The cold lead's going to get a bit hotter. The hot lead's going to get a bit colder. And this equation is going to give us the ratio of the masses needed in order to achieve the 380 degrees Celsius, which is our target. So here we have minus 250. We can cancel C from both of these because we're mixing in two lots of the same liquid. So the specific heat constant is irrelevant in this question. It actually cancels out. Change in TH. This is how much the hot temperature is going to change. So this is actually going to decrease, right? We're going to have the temperature going from 450 down to 380. So this will be times minus 70 because the temperature is decreasing. This has to be equal to the mass of the cold added, that we don't know, multiplied by its change in temperature. Now we know the cold stuff is going to get hotter. It's going from 330 up to 380, so that's actually going to be plus 50. Now if we just divide both sides by 50, this will give us 250 divided by 50 is 5. So we have 5 times 70 because the negatives cancel. This is equal to 350. And this is going to be the number of kilograms of cold material we are required to add in order to cool the hot lead down to 380 degrees. So here we used the Q equals MCAT formulas in order to do this. Because we were adding lead to lead, the C values in here, these specific heat-related values, actually got cancelled out. If you're adding one material to a different material, you would have to keep track of these C values when solving this equation as well. So these equations can get much more complicated. You can have mixtures of multiple different things, and then you have your heat loss equals heat gain. Then you might have multiple different unknowns. You may need to build other equations in as well. In this case, we were just mixing 2 lots of lead, right? So this was lead and lead. And so these equations simplified quite nicely. And we were able to find that the answer was 350 kilograms.